Ladies and gentlemen, welcome. It's chapter 14. We're starting it on probability in our journey through AP statistics here. We've got this section, about 4 weeks of probability to help us make decisions about how probable events are. That's going to help us with our last section, inference, where we start talking about how far away an observed effect needs to be before we can call something statistically significant. Okay, but we need to know things about probability before we can make that decision. So let's jump in and talk about probability. So first up, let's talk about what a random phenomena is. Okay, so when we say that something is random or a random phenomenon, we're talking about a situation in which the different outcomes could happen, but we don't know which particular outcomes did or will happen. So for example, a coin flip, okay? A coin flip is a random phenomenon because while the coin is resting on my thumb, you don't know that when I flip it, if it's gonna land as a heads or a tails, right? It has two different options. And while we can guess, and we can have a fairly decent guess as to which one's going to show, I can't tell for certain, right? Because the event is random, right? What is happening is going to be random, okay? So a coin flip, these things are a random phenomenon, things that we don't know when it could be several different outcomes, right? Let's get some vocabulary out of the way here. In general, each occasion upon which we observe a random phenomenon is called a trial. So a single coin flip would be a trial. For each trial, we note the value of the random phenomenon. We call that an outcome. In the terms of the coin flip, this would be heads or tails. Okay, so that would be the outcome of the trial. And then when we combine outcomes, the resulting combination is an event. Okay, so and then all possible outcomes, everything that could happen is called the sample space. So for a coin flip, the sample space is heads and tails, right? If we're talking about a dice roll from a D6, that's a 6-sided die, the sample space is 1, 2, 3, 4, 5, 6, right? These are all the possible outcomes from that. So that's called my sample space. So we've got a few words there that we're going to use to describe things when we're talking about dealing with random phenomenon. The trial, where we observe the occasion in which we observe the random phenomenon. The outcome of that, when we combining the outcomes, that's the event. And then all possible outcomes, like a list of everything that can happen, that is my sample space. All right. We need to talk about the law of large numbers before we go too far, because this is kind of the basis in which we believe that probability works, right? So first, the definition of the law of large numbers is that when we're talking about combinations of outcomes, things are simplified if the individual, sorry, this isn't the definition. When we're thinking about combinations of outcomes, right, things are much more simplified when we're talking about things that are independent, meaning that the outcome of one trial doesn't influence the outcome of another trial. This is not always a safe assumption to make, by the way, but for our first introduction here, we are going to talk about this in terms of independent events, right? Coin flips are independent events because my third coin flip is not influenced by my second coin flip. I could do 5 coin flips in a row, and the 6th one is still not influenced by the results of the previous 5, so they're independent, okay? What the law of large numbers says is that in the long run, the relative frequency of repeated independent events gets closer and closer to a single value. And that single value that we find is the probability of an event. So again, let's think of it in terms of a coin flip. If I were to flip a coin once, I would get either heads or tails. And if I were to base my probability on that, I would say that I have a 100% chance of getting a heads or a tails, and that's wrong. if I flip a coin twice, I would get either 100% heads because I've got 2 heads in a row, or I would get 50% heads and tails. So I don't actually know which one it is. In order to narrow down that number, I need to do a long run frequency. Like I need to see what the results are over the course of time. 100 coin flips might give me a closer number, but we're still talking about something that's probably going to be between 40 and 60, right? Whereas we know with a coin flip there's 2 options, and those 2 options are basically equally likely to happen. Not exactly, right? There's some studies that have shown that they can't, and there's the possibility of a coin landing on its side, which does happen. I've done it, and it was amazing. But so it's not exact, right? But we need a long run. Like 100's not enough. Like 1,000, maybe 1,000,000. Now we're talking. We need a really long run frequency to be able to tell what the probability of this event is, and we call this empirical probability. When we're actually observing events, we call that empirical probability. On the flip side of the law of large numbers, we have this thing called the law of averages, which, by the way, doesn't exist, right? It's non-existent. This thing is not real. Even though we think it's real, it's not real. The large law of numbers says nothing about short-run behavior, okay? Relative frequencies even out only in the long run. And we're talking about a really long run. In fact, it's infinitely long if we really want to get into the details. What the law of averages says is that when a random event hasn't occurred in a while, we think that that random event is due to happen. So, for example, coin flips. If I were to flip 1 heads in a row, you're probably okay with that, right? That's a fairly likely event. We're also not very uncomfortable with flipping 2 heads in a row. We might, on the 3rd coin flip, start to feel a little bit weird about having 3 heads in a row. But as we get to 4 and 5 heads in a row, as humans, we're going to start being suspicious that something is up, right? When I get 5 heads in a row, I might start thinking, well, there's something wrong with this coin, because this is a really unlikely event to happen. And so that means, because I have 5 heads in a row, that the next one is got to be tails, right? Because I have 5 heads in a row, the next one has to be tails, because I haven't gotten tails in a long time. But this law of averages doesn't exist. The probability that this is going to be a heads or a tails on the 6th one is the same as it was for every single other one, right? That individual probability. And so now I've got 6 heads in a row. And so the 7th one, we think, man, like this is so unlikely to happen. Getting 7 heads in a row, it's not going to happen. I have a lower probability of getting a heads now. And that's false, right? It's still false, because it doesn't matter how many heads in a row I've gotten. Every heads that I get, every coin I flip, still has the same chance of being heads. And we take this run too far. Like, we take it in sports, and we take it in like even politics, that we think that if an event continues to happen, that it's changing the probability that's going to happen, and it's simply not true. Okay, so this law of averages does not exist, and it's a very tempting thing to think, but it's not at all true. Okay, as long as the events are independent. Okay, again, as long as the events are independent, it's simply not true. All right. So, law of large numbers, law of averages, we kind of like, we think about those things, but let's talk about some actual theoretical probability modeling here. So here's a really basic explanation of what probability is, okay? This over here, by the way, this notation is very important. We do say that the same way we say function notation, that's P of A, but what that means is the probability of event A. And you will find that as you go through some of these videos that I make for probability, I really focus on getting this notation correct for a particular situation. Probability can be tough because of the language we use. It has to be very precise. having very precise notation and understanding that notation is essential to be able to doing good probability, right? It really helps align those two things, the language and the calculations, okay? So keep that in mind as we go, right? There's going to be a heavy focus on making sure our notation is correct. But basic probability is just this, the number of outcomes in A over the possible number of outcomes, right? To flip a heads, right, P of heads is going to be 1 because there's one way to get it, over 2, or basically 2, because that's the side thing not really possible, but it's possible, but it's very, very rare. It's basically 2, right? 1 and 2. So the probability of getting a heads is 1/2 because there's one way to get a heads and it's equally likely as the tails. So there's 2 possible outcomes. Okay, so very basic probability there, but let's talk about some more specific rules because we can augment that and make that a little bit definitely a lot more complex. But first of all, rule number 1: probability is a number between 0 and 1. Okay, so mathematically, what that says is the probability of event A is between 0 and 1. That might be 0.59, right? Which we, by the way, equate as 59% typically. But you can't have 110%. It's impossible. What that would mean is that you have more, to think about it in terms of this thing here, that would mean that we have more possible outcomes in A than total number of possible outcomes. And that's ridiculous because if possible A has 10 ways of happening, we can't have 9 possible outcomes because A has 10. So this has to be a number between 0 and 1. Otherwise, simply doesn't work, right? Probability has to be between 0 and 1. Rule number 2, the probability of all, the set of all possible outcomes has to be 1. That is P of S, S representing the set of all possible outcomes, which, by the way, we called the sample space, the probability of the sample space. Is 1. So here's a nice picture of that as a Venn diagram. This is my sample space, S. It is all the possible outcomes for this particular event. And it has a probability of 1. Combined, all possible outcomes have a probability of 1. If all possible outcomes have a probability over 1, then we have something wrong because that can't happen, right? Because of our initial definition of probability. Number 3 is called the complement rule. The set of outcomes that are not in the event A is called the complement of A, denoted as a complement. We can also sometimes just call that not A. Is the same thing as a complement. Mathematically, the probability of an event occurring is 1 minus the probability that it doesn't occur, right? Think about what we just said with our sample space there. If this is A, if this circle is event A, and the box is my sample space, that means everything else is a complement. Well, if I think of this as a big area model, if I know the probability of A, if I know the area of A, I can take, to find a complement, I can take 1 minus the probability of A. And the other way works as well. If I want to know a complement, the probability that something doesn't occur, I can take the probability that it does occur and subtract it from 1. And that will give me the probability that it does occur. Right? So the complement rule we can calculate mathematically by doing 1 minus the probability. All right? The addition rule. Now here we have to define something about 2 events. When events have no outcomes in common, meaning they can't occur at the same time, they are called disjoint or mutually exclusive are those words. So here's a picture of what it means to be disjoint. Notice that this is event A in this Venn diagram. This circle is event B. There is no overlap in A or B, meaning there is no case where you can be both A and B. For example, let's say we're talking about probability of being a freshman or being a sophomore. You cannot be a freshman and a sophomore at the same time. You can't be a froshmore or a sophman, right? It doesn't work. So those events are disjoint, okay? Being a freshman, being a sophomore are disjoint events because you can't do them both at the same time. When joint events are disjoint, we can calculate the probability by adding the two probabilities together. That is, P of A, and this is the OR symbol, P of A or B equals P of A plus P of B. And again, this only works when A and B are disjoint. So when you have disjoint events, you can add the two probabilities together. Finally, let's talk about the multiplication rule before we do some examples. For two independent events, right, events that don't influence each other, A and B, the probability that both A and B occur is the product of the probabilities of the two events. So here we have P of A and B is P of A times P of B. And again, that's provided that they are independent, which is not always a safe assumption to make. But if they are, P of A times P of B gives you P of A and B. These two independent events, A and B, are not disjoint as long as the two events have probabilities greater than 0. So here's a nice picture of that. We've got some overlap here, which means they're not disjoint. So when I multiply the two together, I should get this area in here, P of A and B. Okay? Independent events we multiply. Disjoint events we add. Let's do some examples. This I've already said this, right? Talking about the independence assumption. We'll talk in the next chapter about what happens when the events are not independent. Okay. So let's do some examples here. Okay. So suppose you were choosing a random student from the hallways. If the probability of getting a senior is 0.32, what is the probability of not selecting a senior, right? In other words, notation-wise, since P of senior is 0.32, we know that P of not senior is 1 minus 0.32, which is 0.668. So P of not senior, or senior complement, is 0.68. Because if the probability of being a senior is 0.32, then the probability of not being a senior is 0.68. Let's continue. You now need to choose a student from the hallways once per day. What are the chances of choosing a senior 2 days in a row? So we've got to think. Are these disjoint events? Are these independent events? Well, if I choose a senior on Monday, it's not going to affect whether or not I choose a senior on Tuesday. Therefore, these two events are independent. And since the two events are independent, I can do the probability of having a senior on Monday and a probability of doing a senior on Tuesday, which is P of senior times P of senior, or 0.1024. Independent events, I use the multiplication rule. And because I'm using the multiplication rule, I'm taking the probability of getting a senior, and I'm multiplying it by the probability of getting a senior, 0.32 times 0.32, and I'm getting 0.1024. Let's look at the next one. Suppose P of senior is 0.32, and P of junior is 0.36. What is the probability that a randomly selected student is a junior or a senior? Are these disjoint events? Can you be a senior and a junior at the same time? Absolutely not. You can't. So these events are disjoint. Notice the key word here also. It says junior or a senior, right? The or is really a key word that you're going to use the addition rule. Since these events are disjoint, you can't be a senior and a junior. You use the addition rule to find the solution. P of senior or junior is 0.32 plus 0.36, which is 0.68. And again, note the notation. The or between the senior and your junior means we're using the addition rule to add them. Let's keep going. We got a bunch of them here, right? Suppose now that the probability of a senior is 0.32, the probability of a junior is 0.25, and the probability of a sophomore is 0.21. What's the probability that a randomly selected student is a freshman? So, are these events disjoint? Yes. You can't be a senior and a junior and a sophomore at the same time. You can't be a junior and a sophomore at the same time. You can't be a senior and a sophomore at the same time. So we're going to add all of these probabilities together. But remember, the question is, what's the probability of selecting a freshman? Well, since these are disjoint, and I can't be all of those things at the same time, I can use the complement to figure this out. The probability of being a freshman is equal to the probability of being a senior or a junior or a sophomore complement. Notice how we're using a combination of the addition rule and the complement rule to solve this, right? The complement of being a senior, junior, or sophomore is being a freshman. So here, and this is kind of written funny here, this is 1 minus the probability of 0.32 minus 0.25, plus 0.25 plus 0.21 equals, and that equals 0.22. Right? I add up the probability of being a senior, junior, or sophomore. I subtract it from 1, I get 0.2. This is written weird with the subtraction symbols where I'm taking 1 and then I'm just subtracting all of those away. So I apologize if that looks a little bit confusing. But so here we're using a combination of addition rule and complement rule to solve it. Let's keep going. What's the probability of not choosing a senior until Thursday? Ooh, okay, so I'm going to choose many seniors in a row. Right? I need to choose not a senior on Monday, and not a senior on Tuesday, and not a senior on Wednesday, but I do need to choose a senior on Thursday. So are they disjoint events? Well, no, they're not, because I cannot choose a senior on Monday and Tuesday, and that's a thing that can happen. So they're not disjoint. Are they independent? Does not choosing a senior on Tuesday make it so that I won't choose a senior on Monday? And that is true. They will not affect each other. So these are independent events. So we have the probability of not choosing a senior being 0.68. And I need that to happen on Monday, Tuesday, and Wednesday. So we're talking about P of Monday not senior, and Tuesday not senior, and Wednesday not senior, and Thursday senior, right? I have to go not senior, not senior, not senior, senior. And these are independent events. So I'm using the multiplication rule to solve this. Not senior, not senior, not senior, senior, which is 0.68 times 0.68 times 0.68 times 0.32. Which is 0.101. So again, notice the logic that we had to do with these independent events, right? We used a combination of the complement rule and the multiplication rule. I had to go not senior, not senior, not senior, senior. 0.68 times 0.68 times 0.68 times 0.32. I think this is my last one here. So what is the probability of choosing at least one senior throughout the week? Okay, so that's a little bit different now. At least one senior. That means that I have to do a senior on Monday or Tuesday or Wednesday or Thursday or Friday, right? I have to choose at least one senior. So it could be that I get one senior all week, or it could be that I get two seniors all week, or 3 or 4. But the only thing that doesn't work is 0 seniors all week. Well, think about the logic here, right? For this to happen, I would need to choose 1, 2, 3, 4, or 5 times. Well, what are my total number of things that I can do? I can choose 0 seniors, 1, 2, 3, 4, or 5 seniors. These are the only possibilities, right? I can't choose 6 seniors because I'm not doing 6 days. I'm either getting 5 seniors, 4, 3, 2, 1, or I choose 0 seniors. Well, I need to choose at least one. These are the ones that I care about over here. This is different. So in order to choose at least one, I'm going to use the complement rule, because choosing at least one is the complement of not choosing a senior all week. So notice the complement that I'm doing here. Choosing at least one, getting 1, 2, 3, 4, or 5, is 1 minus choosing 0. So if I can find the probability of choosing 0 and take the complement of that, I'll have my probability of at least 1. So I need to have not senior on Monday, not senior on Tuesday, not senior on Wednesday, not senior on Thursday, and not senior on Friday. And I need to subtract that from 1. So that's 1 minus 0.68 to the 5th power, which is 0.854. So with the at least words there, I had to use the complement rule again in order to solve it. So, couple of last words here. The phrase at least is almost always a tip-off to think about the complement. Something that happens at least once does happen. But happening at least once is the complement of not happening at all. And that's a lot easier to find. Not happening at all is easy to find. Okay. A couple of other notes. Not, when you see not, that generally means subtract from 1. When you see the word or, that generally means to add. And when you generally see the word and, that means to multiply. All right. We're going to have some practice problems in class on this one. If you've got questions, comments, concerns, please leave them as comments here, and I will definitely do my best to help you out, or go talk to your teacher. They're the best resource that you can have, okay? So thank you very much for watching this video, and I hope you guys have a good day. All right, bye.